Hey everybody, welcome back to chemistry. And so now what I'm going to do is talk a little bit about how we classify matter in terms of composition. So how we do that is covered in chapter 1.1 of your book. Here in general, what we do is we subdivide matter into two kinds of chunks. One kind are pure substances and another kind are mixtures, and I'll talk a little bit more about that. And then at the very end of the presentation, I'll talk a little bit about physical versus chemical changes and physical versus chemical properties. Okay, so let's talk about subdividing matter in terms of its composition. So what we have here is kind of a flow chart of how we do this subdivision of matter. And so you see matter on top. And so in a way I'll describe in a bit, we can sort of subdivide this matter into either a pure substance or a mixture. Now going to the left, you see pure substances can be one of two things. They could either be elements or they can be compounds. I'll talk a little bit more about mixtures later. Let's just kind of focus on pure substances now. So a pure substance is either going to be one of two things. It either can be an element or a compound. And so what an element is a single type of atom or molecule, and an element cannot be broken down further and changed into something different with different properties. In other words, it can't be broken down in any way and changed into a new element, for example. Now, a compound is where you have two or more different elements combined. And one way you can tell you have a compound is you can put it under some ordinary chemical means and see if that compound maybe changes into something else. Maybe it changes into two different elements. So an example of that is sort of sodium chloride, as you know, is composed of sodium and chlorine bound together. And so because there are two elements bound together, it is a compound, but you can apply a voltage to sodium chloride, and what will happen is you'll get sodium released from the chlorine. And so the sodium and the chlorine, they have their unique properties which are different than the properties of sodium chloride. And so that's sort of a simple test to see if you have a compound, is if you can break it down into simpler elements, then that would be a compound. So I'm going to talk a little bit more about elements and compounds here. Just to remind you that elements are seen in the periodic table, and we have about 100 different elements. And each of these elements has different properties. However, for each element, it has its unique properties, but it cannot be further decomposed to another different kind of element. So I have some examples of elements there, and you would see these in the periodic table. So you would see oxygen and sodium and uranium, and so those are all found in the periodic table, and they have different properties. On the other hand, another kind of pure substance would be a compound. And so compounds, again, are made of different elements bound together. So I have sodium chloride there as an example, which I just talked about. Carbon dioxide is a compound because it has two different elements bound together. Two oxygen atoms are bound to carbon. And table sugar, which is a compound that has three different elements, carbon, hydrogen, oxygen, and they're in those proportions that you see in that slide. Okay, so now what I want to do is I want to draw pictures of little bits of matter and figure out whether the matter is either atoms or molecules or elements or compounds. So first off, what I want to draw is this. So I have a nitrogen atom here bound to another nitrogen atom, and so we have another one of these I'm drawing like this, and another one of these that is drawn like this. So first off, what is this? And so what you can see is that these bits are nitrogen. So we're going to write out a formula here for that, which is N2. Now let's look at the pictures and figure out whether we're looking at atoms or molecules. And so what you can see is we don't see so much individual nitrogen atoms in space here. What we see are little particles that have two nitrogen atoms bound together. We cannot say that these are individual atoms. Instead, we have a particle with more than one atom bound together. We have two atoms bound together, and so this must be a molecule. And so the next thing that we need to figure out, is this an element or a compound? So what I see here is that this is not a compound. The reason why I know it's not a compound is because I don't see two different elements bound together. Instead, I look at all these particles and I see it's the same element despite the fact that the particles have two of the atoms stuck together. If it's the same element in these particles, this is an element. So the next thing I want to look at is sodium chloride. So I'm going to draw a picture of that now. Well, you have a sodium ion. I'm not going to draw the charge for the ion, but just know that it is there, bound to a chlorine ion. And so what you probably know is that in a grain of salt, you just don't have a single sodium bound to the chlorine. You have a matrix of sodium chloride ions stuck together like this. And going on in 3 dimensions. And so what is this? This is sodium chloride. I'm going to write the formula here, NaCl. Now, is this an atom or a molecule? Well, you have 2 atoms stuck together, sodium chloride, and then there are other atoms that are kind of close by, if not stuck together, to the first sodium chloride. So this would be considered a molecule. This is definitely not free atoms by themselves. Is this an element or a compound? Well, what I'm hoping you'll see is that this is a compound because we have 2 elements here in this substance, and so this is a compound. Now I want to talk about another gas that's in air. So air is 78% nitrogen, 21% oxygen, and then the next most predominant gas in air is a gas called argon. So let's draw out what argon might look like. So with argon, you really don't have 2 atoms bound together. Instead, you have single atoms like this. And so this is argon gas. Again, it's a small component of air. Is this an atom or a molecule? Well, since you have single atoms by themselves, this would be considered an atom. Is it an element or a compound? Again, each of these atoms are 1 element, so this is considered an element. Now, another molecule that might be in the air, but you hope isn't, is a pollutant called nitrogen dioxide. So let me draw a structure for that. So we have N, O, O, and then let me draw another one, N, O, O. So this is nitrogen dioxide. So this is NO2. And so is this an atom or a molecule? And what I'm kind of hoping you'll see is that each of these individual units are 3 atoms stuck together. So this should be a molecule. And then are these elements or compounds? Again, these individual units, these molecules have more than 1 element, and so they should be compound. Okay, and the last thing I want to remind you of, which is pretty important, is that both elements and compounds are pure substances. So I just talked about elements and compounds as being pure substances. And so now what we're going to do is talk about mixtures. And what mixtures are where you have 2 or more pure substances mixed together. So it could be, say, 2 elements mixed together, or it could be 2 compounds mixed together, or it could be an element and a compound and another element mixed together. So those would all be mixtures. Now, how they separate themselves or not in the mixture determines whether it's heterogeneous or homogeneous. You can say the word homogeneous if you want. Another word that is used is homogeneous. I tend to use homogeneous. So what is a heterogeneous mixture? A heterogeneous mixture would be where you have 2 or more pure substances mixed together, but they're not mixed very well. And so maybe you have one of the pure substances settling out away from the other pure substance. So a very good example of that would be sand in water. If you put sand and water in a glass, what would happen over time is the sand will settle out of the water. So how do we kind of know it's a heterogeneous mixture? So one thing we can see is that there's sort of 2 parts to it, but the way you test to see if it's a heterogeneous mixture is you sample at different places. If the samples have the same properties wherever you sample them, then that would be a homogeneous mixture. However, if you sample, say, up top and you get mostly properties of water, but you sample somewhere else, say the bottom, and you get properties mostly sand, that would be a heterogeneous mixture. Another example of a heterogeneous mixture is if you have a glass of water and you pour in tons and tons and tons of sugar such that sugar settles out in the bottom of the water. So that would be a saturated solution of sugar water. So at the top of the solution, it has certain properties that of sugar dissolved into the water, but on the bottom it's mostly sugar, which has its different properties, and therefore that would be considered a heterogeneous mixture. Now, let's say instead of pouring a ton of sugar in the water, you just poured a little bit of sugar in the water. And if you poured a little bit of sugar in the water, maybe all the sugar completely dissolves in the water, such that the sugar is not settling at the bottom of the water. In that case, then wherever you sample your sugar water, if it's all the sugar is dissolved in the water, it's going to have the same properties throughout. So if that is the case, that is a homogeneous mixture. Okay. And so I just kind of mentioned that, what I just talked about there, kind of in long form. So moving on. Another thing I need to mention to you is that homogeneous mixtures are also called solutions. So there are a lot of different kinds of solutions. So these solutions can vary in terms of phase. So for example, one solution you know of already is that where you dissolve a solid in a liquid. But other solutions are where you dissolve a gas in a gas, for example, or another solution is where you dissolve a solid in a solid. If you, in these mixing of the phases, create a homogeneous mixture, that is a solution. So let me just kind of mention some examples of this really quick. So if you have a gas mixed with a gas, can you think of a simple example of that? And a simple example would be air. So there you have nitrogen gas mixed with oxygen gas with a little bit of argon and other gases mixed in there. So that would be a solution. And so air, because it is a solution, is also a homogeneous mixture. So a solid dissolved in liquid, so we can think of a lot of those. So for example, maybe we have salt in water. But again, make sure that you know whether it's homogeneous or heterogeneous. It is homogeneous if you just dissolve a little bit of salt in the water so you have the properties the same throughout the sample. But if you dissolve so much salt that there's salt on the bottom of the water, then you have a heterogeneous mixture. Now, are there examples of solids dissolved in solids that are homogeneous mixtures or solutions? And the answer is yes. So one example we just mentioned was a penny. This is actually brass. So what brass is a mixture of two elements, copper and zinc. And so before 1982, the pennies were mostly copper with a little bit of zinc. But after 1982, they switched that proportion, so they're mostly zinc and a little bit of copper. But because they are mixtures of zinc and copper, they are considered homogeneous mixtures or solutions. And they're all considered to be brass. Another example of a solid dissolved in solid would be bronze. So bronze is not a mixture of copper and zinc. It is a mixture of the element copper and the element tin. And so you can vary the amount of copper and tin in the bronze. One person found out that when you mix tin with copper, it makes the copper much stronger. So bronze was often used in armaments in the past. Okay, so let's move on. Okay, so what is the matter classified as? So we'll try to go through this pretty quickly. So on the top left here, I have a picture of granite. So this is granite. And so it looks like the granite has two or more pure substances. And so we have a white substance, which is quartz, and we have another substance, which is black, which is mica. And so the quartz and mica are both compounds. So we have two compounds mixed in here. So we have two substances mixed in here. However, what you can see, they're not mixed very well. So if you were to sample a certain portion of the granite and hit the black spot, you would be sampling the mica, which would have specific properties. If you were to sample a white spot, you would be sampling quartz, which would be different properties. So this would be a mixture, yes, but it's a heterogeneous mixture. Okay, the next sample we have there is a piece of gold, and so you may know that gold is an element. So this is gold. and this is an element. So here we have a penny, and I just talked about how penny is made of a mixture of copper and zinc. And so as you can imagine, that the copper and zinc is so thoroughly mixed together that that penny is going to have the same properties no matter where you sample it. So this is considered a homogeneous mixture. Okay, and so the next picture there is a picture of table salt. And so you probably know that table salt is sodium chloride. And so sodium chloride is a pure substance, but it is comprised of two different elements bound together. So this should be a compound. Okay, next we have a picture of one of the elements in the periodic table. This element is chlorine, and so this would be considered an element. So what we have in the next picture is sugar being dumped into water, and so far the sugar is not thoroughly mixed in with the water. So it is a mixture because you have two or more pure substances being mixed, which are the compound sugar and the compound water. But because they are not thoroughly mixed, this would be a heterogeneous mixture. So this is sugar, water. And so you have the same thing here, but now very thoroughly mixed. And so as you might imagine, if you were to sample the top part of the sugar water versus the bottom part of the sugar water, it will have exactly the same properties. For example, it would have the same density, and it would probably taste the same level of sweetness. So this would be a homogeneous mixture. And then the last picture is a picture of potassium bound to chlorine. And so this is the potassium chloride salt. So this is a pure substance, and we have two elements mixed in, so this must be a compound. Okay, moving on. So now I'm going to talk about a physical and chemical change. So what a physical change is a change in the matter that does not change the identity or the composition of the substance in the matter. So let me give you some examples of a physical change. So one example of a physical change would be melting. So if you melt water, you're taking it from the solid phase to the liquid phase. And so it is water, or H2O, in the solid phase, and then when it melts to liquid, it is still water, H2O. So there is a change in the phase of the water, but that change has not changed the identity of the water. So that would be a physical change. Another example would be, say, dissolving a piece of matter in water. So for example, let's say you have sugar and it has its particular properties, and let's say you dissolve that in water. So the form of the sugar is changing because it's dissolving in the water, but the sugar in the water in and of itself has the same properties. And the way you could test that is you could boil off the water and get the remaining sugar, and what you would find is that the sugar, after you boiled off the water, has the same properties as the sugar you had putting into the water. And therefore, dissolving the sugar in water, that would be a physical change for the sugar. On the other hand, a chemical change is different. A chemical change is where you take the matter, and then when it goes about its change, it changes the identity or the composition of the matter. And so there are some interesting and fun examples of that. So a good example of a chemical change would be combustion. So combustion can, of course, happen to a lot of things, but here we have an example of combustion occurring to wood. So wood is mostly made of carbohydrate, and so it's a bunch of carbons and hydrogens and oxygens bound in a particular way. If you expose wood or carbohydrate to oxygen with a lot of heat, it will undergo a chemical change. The reason why we know it's a chemical change is because the products after it undergoes this change are different than the carbohydrates that we had before the change. So the wood is carbohydrate before the burning, but after the burning, the carbohydrate is gone and you've created new molecules. You have created carbon dioxide and water. So that would be a chemical change. Another example of a chemical change is if you have iron. And iron is an element, and let's say you expose the iron to oxygen and a little bit of water mixed in as well. What will happen is, in the presence of the water, the oxygen binds very tightly to the iron, binds it chemically to the iron and changes the iron's properties so that it's no longer iron element, but now it's a new compound called iron oxide, which is also known as rust. So this would be another good fun example of a chemical change of here iron being turned into something completely new, rust, which is iron oxide. And then here, bad cooking skills. And so that's probably a picture from my kitchen there. So if you happen to burn your carbohydrates in your bread and you're turning it into something new like elemental carbon like I did, well then that would be an example of a chemical change. Okay, so moving on. So the last thing I'm going to talk about is the difference between physical and chemical properties. So a property is a characteristic of matter, and so there are a lot of properties that matter can have. Matter will have a certain color, it will have a certain level maybe of flammability, it has a certain boiling point, it has certain reactivity with acid, it might have a certain melting point, and other properties that I could mention. So of those properties, some are going to be physical properties and some will be chemical properties. What a physical property is as follows. You test for the property. It is a physical property if in the process of testing for the property, the identity of that matter does not change. On the other hand, if you test the property and for some reason the identity of the matter changes, then that would be a chemical property. So let's say you're looking at the color of the shirt. So let's say I'm wearing, well, I am wearing a blue shirt right now. If someone were to test that property, the color of the shirt, by looking at my shirt and they determined it was blue, did that process of looking at my shirt change the color of the shirt to something like red? No, it did not. So color is a physical property. Another good example of a physical property is determining the boiling point of water. And so you would heat up water and it would get warmer and warmer, and at some point it would boil. And then when it boils off, is it still water? Yes, it's just in the gaseous vapor state. So that is another example of a physical property. A good example of a chemical property would be flammability. If you're testing the flammability of a substance and it burns, as we kind of talked about earlier, when it burns, it changes into a completely new set of molecules. And so since it's changing into a new identity, then that property would be a chemical property. Another good chemical property is reactivity with acids. A lot of metals can react with acid, and when they do, you basically break up the metal into pieces and you get the metal binding with one of the atoms in the acid. And so when that happens, you're changing the metal's composition. And so reactivity with an acid would be considered also a chemical property. Okay, to finish up, I want you to take a look at this. And I want you to tell me, just looking at the pictures, can you distinguish between a physical change or a chemical change? So let me talk about a little bit of what's going on. So in picture A, we are boiling water. Is that a physical change or a chemical change? In picture B, we are taking iron and exposing it to oxygen in the presence of water to form something else. Is that a physical change or a chemical change? Okay, I'll leave you at that. Thank you for listening.